Hello, good afternoon, everybody. We are about to start paper session 21, Algorithms in the Wild, that features five very interesting presentations. As usual, we will do the five presentations and then the Q&A at the end of the presentations. Brian Su? Brian, can you come? Brian? Hey.
Okay, sounds good. Okay, and how do I control this? Okay, sounds good. Hey everyone, thank you all for being here. My name is Brian. I'm an AI engineer at LinkedIn, and really excited to be here to present our paper, Disentangling and Operationalizing AI Fairness at LinkedIn. And so the high-level view of this paper is I'll go over some of the tricky topics of how we actually handle fairness, how we juggle the problem of equity versus equality, what specific mathematical fairness definition we actually look at and measure, and such topics. And it's great to be able to present this publicly because before, if you asked me about what we actually do at LinkedIn, I'd have to kind of dodge the question, but otherwise the lawyers would get mad at me. But now half of our author list are those lawyers, so they can't complain. I also want to just quickly preface, I want to give a lot of examples here, so I'll be using male, female as examples, but of course, gender is very complex, and I just want to note that all the things I discuss generalize to non-binary groups as well. So to begin, you might ask yourself, what does fairness look like? Well, imagine that you're a recruiter and you make a search, and you find that out of 100 candidates, you see that 80 are male and 20 are female. And so you can ask yourself, is this unfair because we didn't get a 50-50 distribution? And on one hand, not necessarily if you take a lens that we call equal treatment, which is to say you may think that as long as the model is correctly predicting for the real world qualifications, as well as it does for males as it does for females, then you have no problem there and the model is fair. So this is commonly called predictive parity as well. But from another lens that we're going to call equitable outcomes, you can say that, well, I also know females have historically had barriers that may have prevented them from obtaining the same qualifications as males, and therefore the real distribution should be 50-50, and anything that's away from that can be considered biased. And so this is commonly called demographic parity. And if you've been in the fairness literature, this is kind of no surprise because there's a lot of these incompatible or mutually incompatible definitions within them. And for this talk, I want to focus on these two perspectives, equal treatment and equitable outcomes, which is really well depicted in this illustration here. And specifically the fact that they have these mutual incompatibilities with each other. So the crux of this talk really is what are we to do about this situation where we have an incompatibility between equal treatment and equitable outcomes. And so our stance is to take a holistic perspective when approaching this topic, in that we want to view things from an equal treatment lens when we're talking about our AI models, but we also need to recognize that that's not the end of the story and that's not enough. In fact, we want to complement this strategy with the equitable outcomes lens when we're thinking about product initiatives. So in other words, AI fairness, we want to see it as a combination of equal AI treatment as well as product equity. And I'll give specific examples of how we're doing that in a bit. But for now, I want to distill these notions into three major principles to illustrate how we can operationalize this across the entirety of our platform. And the first one is exactly that when we're thinking about AI products, we want to take an equal treatment lens and make sure that the models correctly predict real-world qualifications equally well across all groups. And second, we also want to avoid just stopping there and make sure that we're thinking about equity when we're designing our products as well, and take an equitable outcomes approach when we're thinking about it from that lens. And thirdly, we'll try to validate our approaches externally and lead with transparency in this field. So to go further into this first principle, measuring and mitigating, we want to take the lens of equal treatment. So what exact mathematical definition are we looking at? Well, it's predictive parity. So in other words, you want the expected outcomes to be conditionally independent of the group given the score. And that's a little hard to think about. Just imagine that if you're in a binary classification setting, if your model predicts something like 0.6, then the expected outcome in terms of something like the click-through rate should have the same interpretation regardless of what group the person you're predicting for belongs to. So you can imagine that such a definition can actually be measured and considered for some of the products like people you may know or people also viewed. And I'll go through a case study of this in a bit. The second principle about how we're going to approach equitable outcomes from a product lens is more nuanced. And here, the idea is that we know that there have been historical barriers for certain marginalized groups, and we want to be sure to design products that can help alleviate those barriers. One example of that is the recently launched Self-ID initiative, where members on LinkedIn can choose to disclose factors about their identity. And one thing we can do with that, for example, is when recruiters make a search, we can now suggest filters to, we can suggest adjustments to their filters essentially to broaden their search diversity when we notice that the results are lack diversity. Another perspective is taking a explore-exploit approach to make sure that our models aren't just reinforcing the status quo, but periodically can reevaluate certain people that we're unsure about. And the last principle is to really be at the forefront of leading with transparency and trying to validate our approaches externally through talks like these. And so we're in collaboration with academia, other industry partners, as well as Microsoft's responsible AI team to make sure that we're really vetting our approaches in this space. So let me switch gears a bit and go from the high-level details to an actual case study that we went through. This is a product you may have encountered if you've used the platform. It's called People Also Viewed, and basically if you go to a member's profile, you'll see some size suggestions. And so this is a major product because it's a huge source of profile traffic on our platform. And the case study, I'll basically cover how we did the measurement as well as bias mitigation and the measurements afterwards in a live setting. Okay, so what is the fairness definition that we're actually looking at? It's called predictive parity again. And essentially, it's like I said before, where we saw that when the model was predicting something like a score of 0.6 in a binary classification setting, it would have different interpretations in terms of the expected outcomes depending on which group it was predicting for. So we sought to mitigate this through something that we detail in the paper as a justifiability framework. And why does it have this name of justifiability? Well, we know from literature that in order to solve these issues of predictive parity bias, one easy way to do that is to just include the demographic inside of the model. But before jumping to that conclusion, we wanted to explore other things as well. So we justify our solution at the end of the day by ensuring that we vetted a sufficient number of other solutions to see if they're adequate in closing the gap or not. And so we ultimately found that post-processing the model with group-level calibration performed the best. And this was a great result in that we launched an online experiment and we saw improvements in both the fairness metric as well as product metrics. So this is a great example where fairness and products can go hand in hand with each other. But there's also other risks involved in such mitigation platforms. Like, for example, in this particular case, we knew that the model would essentially be increasing the scores of female members. And while this is generally a good thing for them, it could also lead to unintended consequences in the sense that, you know, if your profile is being listed higher, that could also subject you to things like more spammy invites or messages that you don't want to see, and et cetera. So we took care to actually do this measurement of seeing if people are indeed getting these more unwanted interactions. And fortunately, we didn't find any. But the important theme here is that, like, for any kind of fairness mitigation that we enact, we'll think ahead to see what kind of unintended consequences can result and measure them accordingly. And so in summary, we've set forth the 3 principles of operationalizing and disentangling fairness. So one is when we're thinking about AI models, we want to take an equal treatment lens and measure metrics such as predictive parity. Second is we'll complement this AI strategy with product initiatives so that we can achieve equitable outcomes. And third is that we'll try to lead with transparency and externally validate our methods and principles. And we also gave a case study in which we showed we were able to both increase fairness and product metrics as well. So that's all I have. Thank you so much for your time and attention. My name is Brian, and if you have any questions or want to discuss this further, feel free to reach out to me through your favorite professional networking platform. Thank you.
Can I go back? Yeah. So, hi everyone. My name is Amélie Marion. I'm a computer science faculty at Rutgers University. And today I'm going to discuss some experience, and I'm going to relate and reflect upon this experience working with stakeholders in the New York City high school matching system, and see how we can gather the power of stakeholders in the system to improve transparency and accountability. So if you're not familiar with school matching, the New York City school matching is a traditional school matching system where you have schools that rank students based on various attributes, on various criteria. And the students rank the schools based on the schools they would prefer to attend. And there's a centralized algorithm that assigns students to school based on some internal policy and tries to optimize the best assignments of students to school. The New York City school matching algorithm is very well known. It's a variation on the Gale-Shapley algorithm, also called the deferred acceptance algorithm, and it was chosen. There's a paper from 2003, I believe, that explains it in detail. It was chosen to be strategy-proof on the side of students, which means that there is no incentive for family to try to game the system. The best approach is always to list the schools you want to attend in your true order of preference. It's also a student proposing version of the algorithm, which means that it gives the stable, optimal student outcomes. Right. But that's the theory. In practice, when you implement an algorithm, there's a lot of implementation choices that needs to happen that may have an impact on the guarantees and on the properties of the algorithm. And in New York City, one of these specific detail is that students are limited to listing only 12 choices. That seems like a lot, but New York City, for instance, for high school, has 400 high schools with 700 programs. And so while the best strategy within your choice list is always to list your 12 choices in your best order of preferences, if you do not list schools for which you have a good chance of being selected, you may end up being unmatched. And what happens when a student is unmatched is that after everybody has been assigned, the Department of Education, the New York City Department of Education, assigns students to schools where you have some space. So this is obviously some undesirable outcome. There are also a lot of different priorities and set-asides that change how the algorithm operates and changes the possible outcomes of the algorithm. And finally, schools, ranking students for schools is actually very costly. Some schools read essays, some schools have to look at grades and so on, and many schools don't rank all the students, which again leads to undesirable outcomes. And then that was what was happening for 20 years. And a few years ago, COVID-19 happens, and suddenly schools couldn't rank students anymore because they didn't have information about test scores and grades for a year or two. And so there were a lot of system changes due to COVID and also due to some diversity push on this part of the Department of Education. And many schools started bucketizing students, either considering all students or considering all students that had an A average, for instance, and differentiating students based on a randomly assigned number, a lottery number. Now, this lottery number is not new in the system. It has always happened. It has always been there to break ties. But suddenly, it became the primary factor for admission to many schools, right? And so, you know, what could you do? There was not much else that could have been done at the time because of COVID. But it completely changed the game for families. The families had an expectations of, given the grades of their students, where they could expect the student to be accepted. And suddenly, all this was out of the window, and it was based on this randomly assigned number. But the Department of Education in New York City refused at first to give families their lottery number. So there are several problems with that. The first is you cannot hold a lottery in the dark. There's no accountability. There's a reason why the Vietnam draft was done on TV, right? And then there's actually a practical problem. For families, they were in the dark, and they could be in a situation where they would select 12 choices that they had no chance of getting into because their student had a bad lottery number, and they would select only popular schools. And so having the information of where you stand in line compared to other students, there's only one lottery number per student, so it's the same number used for all the schools. So you're in the same order for the schools, will help design your list and avoid being unmatched. And as it turned out, this became a real problem in 2021 and 22, where in some parts of Manhattan, you had almost 20% of students who ended up being unmatched. And so we talked to the Department of Education and asked them to give the lottery numbers to families so they would know what to expect and would, if you had a good number, you would apply to a popular school. If you didn't have a good number, you wouldn't. And they blocked. They didn't want to do that. They just assured us that the numbers were truly random, and I was working with elected parents, and that they would not give information to families because being admitted to a school depended on other students' choice, which is true, but still, knowing where you stand in line does give you some information about your chances. And my favorite, they could not share the numbers with families because it consisted of long strings of numbers and letters that they, the families, could not understand. Challenge accepted. So we worked on the FALL campaign. FALL is the Freedom of Information Law. It's the New York State version of the Freedom of Information Act. Turns out that parents are allowed to have information about their child's chance at the school. It's part of the academic record, FERPA record of the child. And we received numbers that look like this. So for those of you who are computer scientists, it's pretty obviously an hexadecimal. It's not that difficult to understand. But the question now is how it's processed. So it's an hexadecimal in UUID format, V4, and you can identify this based on the pattern of the number, and this is typically created by a random generator. So the numbers seem to be truly random. But we were trying to figure out how they were processed. So I created surveys where I had many families answer the first surveys. The first year I had 136 answers for high schools. And comparing students who got in the school and students who didn't get in the school, it was pretty easy to identify that the lottery numbers were just processed from left to right in a lexicographical order. So the best number started with 0, the worst number started with F, and then you go on and on. So parents just needed to look at the first or 2 characters of their lottery number to have a good idea of the chances of their student, right? They could understand what was happening. So we pushed, and finally, this year, every family got access to their lottery number before applications were due. But the DOE did not communicate it well, and there's still a lot of issue there. So these are some of the numbers, the statistics of the survey. What is interesting is, as this project built on about 3 years, more and more parents started being aware of the lottery numbers and started reading some of the Medium posts I wrote, and I got a lot of feedback from parents how that information was really useful to create their ranked lists. Okay, so let's move on. So there's a lot more in the paper, but highlights and lesson of the survey, there's a real, it's really important for students to have this information to be able to create their list. Otherwise, they waste time actually going to open houses or putting their hopes up for schools they have no chance in attending. And it was very clear for students that their lottery number would be part of why they would be selected for a school. And there was a lot of cases where students wasted time writing essays for schools where they had no chance of attending. For instance, there was one school that had, because it had a continuing student priority, it had no seats for students who were not continuing students and didn't qualify for the low-income set-aside. And thousands, and I'm not joking, thousands of students, it's one of the very popular schools in New York, applied to that school, wrote essays. Their essays were graded by teachers at the school, all for no seats for that particular category. So there's a lot of inefficiencies and dysfunctions in the system that we're able to identify through this project. And not knowing the information about your lottery number result in the loss of trust in the system. And not only the families wasted resources, I said the school wasted times ranking students that would never be able to attend because they didn't have a good enough lottery number. And so as conclusion, we can see that gathering the power of stakeholders and working as a group, we can push public policy decision makers to make systems more accountable and transparent, and use our collective influence for that. In the case of school matching system, better transparency and communication has been proven to improve outcomes. There's some work in China that shows that when students know their test scores before ranking the schools, they make better choices. There's a lot of negative self-selection in underrepresented students as well. So having this information can only improve the outcome for everybody, but that only works if it's well communicated. As of now, the communication is mostly done through parent groups and reading blog posts I wrote, but it's not communicated well by the entity, the Department of Education. Thank you.
Presentation. So the next presentation is also about an algorithm in the wild applied on children. Many of you are familiar with it, perhaps, as the Allegheny County has been a subject of numerous studies. Marisa will do the presentation.
Hi, everybody. My name is Marissa Gerchik. I'm a data scientist at the American Civil Liberties Union, and I'll be presenting our paper, The Devil is in the Details, Interrogating Values Embedded in the Allegheny Family Screening Tool, which was joint work by a team of data scientists and legal professionals at the American Civil Liberties Union and the Human Rights Data Analysis Group. So in this work, we audited a tool used in the child welfare system in the US. So I'll first provide some background about the child welfare system and the tool, and then dive into our audit approach and findings. A large body of work has demonstrated the harms of the child welfare system, including how it surveils, criminalizes, and separates marginalized families, and treats the impacts of structural inequality as the result of individual failings. More than 1 in 2 Black children in the United States will be subject to a Child Protective Services investigation, and more than 1 in 10 Black children will be separated from their parents and placed in the foster system by the time they're 18. And in recent years, advocates have raised concerns about how predictive analytics tools could facilitate this broad family surveillance. As of 2021, child welfare agencies in at least 26 states and the District of Columbia had considered using predictive analytics tools, and jurisdictions in at least 11 states were actually using them. The tool we specifically looked at here was the AFST, used in Allegheny County, Pennsylvania, which includes the city of Pittsburgh. The AFST operates at the screening stage when a call screening worker has to make a decision about whether to investigate an allegation of child neglect that comes through a county hotline. And the AFST works by estimating the probability that a child will be removed from their home by the county and placed in foster care within 2 years of being referred to the agency. The training data that was used to build the tool included information from past referrals to and investigations by the county, medical records, and interactions with the juvenile probation system and other government systems. There's been a lot of prior work on the AFST, including by many of the folks in this room, which has looked at its role in the county's child welfare processes, examinations of its design, its performance and deployment, and its impact on racial disparities in the county's decision-making systems. For this audit, we analyzed de-identified data produced in response to a data request by the Allegheny County Department of Human Services, which included data from 2010 to 2014 that was very similar to the training data for the second version of the tool, and 3 months of production data from 2021 when that version was actually deployed. Additional details about the design of the tool and some of the changes that have occurred between different iterations of the tool are described in a model card that we created for the AFST as part of our audit, which is included as an appendix with our paper. Next, I'll talk about our audit approach. So a growing body of work has focused on understanding the use of algorithmic tools across various domains as encoding policy choices, building on work viewing technical systems as value-laden artifacts. And this work often posits that the designers of algorithmic systems don't work in isolation, but that they can function as political actors and that they can make decisions that can contribute to the harms of machine learning systems. And so we use this framing for our audit, and with that framing in mind, we looked at 3 values embedded in design decisions of the AFST. We ultimately argue that these design choices can function as policy decisions, and they can exacerbate the harms of structural discrimination for already marginalized communities. So the first value we looked at is one that we refer to as risky by association. And this basically has to do with how the model's outputs are aggregated. So to understand what the outputs of the AFST might look like, imagine a hypothetical family with 3 children referred to the county agency. So the AFST would generate individual predicted probabilities and risk scores for each child on the referral. But that's not what the call screener ultimately sees when they're making their decision, because there's an aggregation process that occurs to these scores. And so what the call screener ultimately sees is a single risk score or a label like high risk, as shown on the right here. And so in this first part of our analysis, we examined these aggregation decisions as policy choices, and we looked at their impacts and potential alternatives to this presentation of the model's outputs. We looked at other ways that scores could have been grouped or presented to call screeners, including if they had just shown 1 score for each child on the referral, rather than 1 for the entire household. And we looked at how those different grouping methods would have affected measures of the AFST's performance using metrics like the area under the curve and the false positive rate. And we argue based on this analysis that the AFST's method of grouping risk scores produces racial disparities and presents a misleading picture of families who are evaluated by the tool, effectively treating them as risky by association. So the second value that we looked at is another design decision, which we refer to as the more data, the better. So one of the county's stated goals in adopting the AFST, as they wrote in a 2018 process evaluation, was to make decisions based on as much information as possible. And ultimately, this information included records from public welfare agencies and behavioral health agencies and programs, including information that references or may be a proxy for a person's disability status. So imagine 2 hypothetical individuals, child A and child B, who look exactly the same in the eyes of the AFST for all of the model's features that don't have to do with behavioral health services. So in this example, you can imagine they have identical values for the features that have to do with previous referrals to this agency, interactions with the criminal legal system, and so on. But for the model features that do have to do with behavioral health diagnoses and services, child A and their family have values for these features which indicate that they have used the county's behavioral health services, but child B and their family have values for these features indicating no such service usage. And a key point here is that this doesn't necessarily mean that child B and their family haven't accessed those types of services. It's possible that they've accessed them through private providers, gotten private care, which wouldn't necessarily be recorded in this data. And so in the paper, we analyzed this scenario to show that child A's risk score could be 0 to 4 points higher than child B's risk score on the 1 to 20 point scale. And we showed that there were real examples of this circumstance, where families had the exact same values except for the behavioral health features, and the family with a record of accessing county behavioral health services ended up with a higher risk score. Finally, we looked at how the AFST includes so-called ever-in features in the model, which indicate whether someone involved with a referral has ever been affected by various criminal, legal, and policing systems. We looked at these features through the lens of algorithmic recourse. And because they're immutable, these features have the effect of casting permanent suspicion, and they offer no means of recourse for the families who are marked by these indicators. And in the data we analyzed, we found that the ever-in features disproportionately affected Black families, and that the AFST could have produced greater racial disparities in screen-in rates than an alternative model design that did not take these features into consideration. So with all these findings as context, we asked the question of whether removing these features would have affected the model's performance in the eyes of the tool's developers. So the area under the curve, or AUC, was a key metric that was used in the model development process. So we retrained the model without these features as candidates and examined the impacts on the area under the curve. There's more details in the paper about our exact specification here, but removing features from the criminal legal system, behavioral health system, and Everin features from the training data would have reduced the AUC of the resulting models on the test set by less than 0.01 in each case, as shown by the table on the right. And so with this finding, we argue that this is an example of model multiplicity, where there are multiple models with different feature sets that achieve similar performance. And so given this dynamic, both the fact that there are these bias concerns and the model multiplicity, we argue that deciding whether to include or exclude these features as candidates is fundamentally a policy choice. Those were the 3 values we analyzed. Finally, I'll talk a little bit about some of the limitations of this work and our conclusions. So we looked at a limited set of design decisions related to a particular version of the AFST here. And so the nuances of our findings may not extend to the design of other tools, even though we think this is a useful case study. We found that choices in the design of the AFST have policy impacts, that they can confuse the interpretations of the model's outputs, they introduce variables that give families no opportunity for recourse, and they may perpetuate racial bias. And they may also score people who have disabilities as inherently riskier. And on top of that, many of these features may add little predictive value in terms of AUC, which was a key metric the model developers used in the design process. So when we view these together and look at them promulgated through the algorithm, we argue that these choices can exacerbate the harms of structural discrimination for already marginalized communities. We think these findings demonstrate the urgent need for transparency, independent oversight, and meaningful recourse for families. These families may have no knowledge of the policies embedded in the tools that are imposed upon them. They may have no ability to know how the tool was used to make life-altering decisions, and they're ultimately limited in their ability to fight for their civil liberties, which we think cements longstanding traditions of how family regulation agencies operate. Thank you for listening to this presentation. This was the great team that conducted this work. There's a QR code to our paper here, and please feel free to reach out if you'd like to talk more about this.
And the next paper is also about the politics, in this case, not the politics behind the design of an algorithm, but the politics behind its analysis. And it will be presented by Gabriel.
Yeah, hi, my name is Gabriel Grill, and I'm a PhD candidate at the University of Michigan School of Information, and I will talk today about a paper called Bias as Boundary Object, Unpacking the Politics of an Austerity Algorithm Using Bias Frameworks. This is joint work with Fabian Fischer and Florian Tschech. In 2018, the Austrian Public Employment Services Agency introduced an algorithmic decision support system that promised to aid in distributing scarce resources efficiently. It is colloquially called the AMS algorithm and was meant to classify job seekers into 3 risk categories to cut support measures for those deemed at lowest and highest risk of long-term unemployment. It was presented as a fair and scientific tool meant to objectify this new allocation process. But this narrative was challenged. Various scholars and activists critiqued the system for justifying austerity politics, discrimination, and a strong lack of accountability. The picture on the right highlights a campaign by the digital rights group Epicenter Works. It is intended to illustrate to a broader audience the situation of job seekers confronted with an inscrutable algorithm that to them feels like a slot machine. That's the picture. Like a slot machine. The Austrian Data Protection Agency forbade the use of the AMS algorithm in 2020, but a court case challenging the decision is ongoing. In this paper, we identify biases of the algorithm using a classification framework developed by Friedman and Nissenbaum and discuss implications, benefits, and trade-offs of using such an approach to critique problematic algorithms. Describing an algorithm as biased can mark it as contentious. For others, it may only be seen as a technical description. In the social sciences, the term is often even rejected, as technologies can never be unbiased. These conflicting valuations of bias highlight the fluidity of the concept, which we define as a placeholder construct for some phenomena understood as distortion. Biases become tangible, usually in the form of either a calculated number or a description of the bias. There are many different ways biases could be conceived. Some may be more useful than others, but ultimately no absolute version exists. We in turn understand these biases as socially constructed. We understand biases also as relational and situated, which highlights how they need to be contextualized to become tangible and debatable. For example, a recognized bias can be experienced as problematic or harmful by one social group while seen as an opportunity for others. We also understand biases as performative, which means once they are conceived and communicated as such, they become ways how people understand and feel failure, injustice, and unfairness. Some problematic biases are hidden and barely noticeable, but once they become known as such, they can turn into bigger controversy. This political understanding of bias motivates our work into how bias can be operationalized in productive and emancipatory ways. Our study of the AMS algorithm is based on internal documents, many of which are not public, provided by the Public Employment Agency. We also engaged with civil society groups while conducting this work, such as job seeker interest groups. The initially published documents by the AMS turned out to not paint a comprehensive picture of the system. We described new insights in more detail in our paper. We learned, for example, an early version of the algorithm was intended to actually focus support on the most risky job seekers instead of reducing support measures for them. To analyze the documents, we used qualitative document analysis as a method, which involved a close reading of the documents and annotating relevant sections. Based on identified technical details, we tried to reconstruct the workings of the algorithm, but were not able to recreate an exact implementation, as we didn't have access to the underlying data. We then identified possible biases of the algorithm and categorized them using the framework by Friedman and Nissenbaum. We illustrate how its 3 basic categories for bias can be traced. We adapted the categories slightly to make them fit the context and added subcategories, of which I present a selection now in the following slides. The technical bias category is concerned with representational accuracy in light of technical constraints or considerations. It attributes accountability to human actors as design decisions are problematized. The variables also fix fluid, continuous realities into supposedly stable and discrete categories. For example, the dichotomous health impairment variable absurdly oversimplifies disability and how it impacts possibilities for work in the labor market, disregarding differences, representational justice in favor of supposed bureaucratic efficiency. The data and framing used to construct the model only represents a limited perspective on the labor market that always insinuates that job seekers are the ones responsible for being unemployed. The emergent bias category foregrounds changing contexts, for example, due to the passage of time or use in spaces it was not intended for. For example, norms, laws, and representations are not stable over time, but constantly change, which affects the reliability of the system and cannot be easily solved through updates, as it may take time until these changes result in stable, measurable trends, if they ever do so. Consequently, the job seekers are increasingly misrepresented over time. The envisioned interface presents counselors with a classification and a score that do not provide much room for interpretation and contestation for job seekers. You can see it there on the picture here. Yeah. In fact, internal instructional materials reveal that counselors are trained to convince job seekers of the objectivity of the algorithm when they question their own classification. After the introduction of the algorithm, counseling may center questionable classifications instead of job seekers' articulated needs. The interface is also meant to aid counselors in this convincing by providing a set of a few rudimentary explanations for certain scores that can be presented to worried job seekers. Most of these are not very descriptive, and some of them even reproduce racist and sexist stereotypes. The pre-existing bias category embodies prejudice, held values, and social orders that seep into algorithmic systems through actions of institutions and individuals. In our case, this analytical bias category sensitizes us to the ways that injustices and inequalities are inscribed in the algorithm and reinforced when it's used in decision making. The data and variables used to construct risk scores also account for historical disadvantages and discrimination in the labor market. Thus, the calculated risk of long-term unemployment of marginalized groups affected by these mechanisms is higher, which means fewer resources for these groups with the danger of a self-reinforcing loop algorithmically optimized to exacerbate inequality. For some job seekers with incomplete data, separate models were created. For example, a model for people with migration background likely concentrates many job seekers with calculated high risk of long-term unemployment in one model, which likely makes it harder for new job seekers assigned to the model to access support measures. We argue that the articulation of bias can enable cooperation across community boundaries because bias can be meaningfully constructed to act as a boundary object. Boundary objects are defined as adaptable to different viewpoints and robust enough to maintain their identity across them, and thereby enabling different groups to work together without consensus. For example, the MS algorithm was initially not perceived as highly controversial. The controversy took off after coefficients in a publicized document were interpreted by interest groups and scholars as indicative of bias. They pointed to the fact that being a woman in the system was a risk factor and that may entail spending cuts for this group. This reading undermined the promised objectivity of the system and mobilized people to further investigate the document, the biases it may show, and question the claims of the agency. The numbers, not intended to be indicative of bias, were reinterpreted as such and then became a boundary object around which disparate groups came together to unpack issues such as discrimination. In the paper, we also discuss in more detail how questions of bias and its recognition and stabilization are also about power. In the paper, we also compare several bias frameworks, point to differences, and discuss how they could be improved. We caution to simply apply bias categories uncritically and problematize several in the paper. We further critique frameworks for putting too much focus on technical issues and thereby overemphasizing the role of individual developers. Our paper shows how organizational conditions, like how chosen variables needed to be convincing to stakeholders, also put bounds on what options are available. The frameworks varied in granularity. We argue frameworks with more specific categories can be useful by providing more contextual and concrete guidance in analysis, yet this can also introduce rigidity and make it easier to fall into the trap of simply following the framework like a checklist without reflection. On the other hand, we argue coarse frameworks encourage researchers to adapt the framework to a context and resist simple application. We argue that biases should be seen as a starting point for further analysis, such as what are deeper historical and social explanations for their emergence, what underlying power dynamics stabilize them, and what can be done to counteract them. We also think interrogating a bias can enable fruitful conversation around what unbiased or natural states are assumed or desired, and if some of the biases should be upheld or abandoned. When bias frameworks are used, it is important for our analysts to be cautious about what they make invisible and prioritize to ensure analysis is reflexive. Similarly, it's important for analysts to be aware of their own positionalities. We argue that as bias frameworks are made and reworked, they should make their perspective and epistemological commitments clearer, focus on more concrete phenomena instead of abstract terms like bias, foreground questions of power and justice, and draw more on relevant fields concerned with the social. There's a risk that these frameworks stabilize certain problematic notions of bias, for example, when they are enshrined in law. The stakes are high in matters of bias and harm, so it is important that the possibilities for emancipatory debate remain open and that frameworks are circulated with this in mind. This entails constructing bias categories so that they can act as useful boundary objects. Thank you.
Thank you. The last presentation of the session will be about the topic that perhaps brought many of you into this research community, which is the study of risk assessment instruments in criminal justice.
Hi, everyone. Oh, I need to work out how to. Okay, let's hope I'll work it out. Thanks for sticking around for the last talk in the last session. Oh, does it automatically go? Okay, so sorry about that. No, this does do it automatically. Sorry. Okay. I'll manage. Great start. So today I'm going to talk to you very briefly about our work in which we sort of study how the training and evaluation of risk assessment instruments is impacted by what we call differential arrest rates. So in case anyone's not familiar, this doesn't work. I'm so sorry. I worked it out. Okay. So risk assessment instruments are algorithmic tools that are commonly used all over the world, but specifically very much in the US, to assist bail and sentencing decisions. And their primary goal is to try and predict how risky somebody is in the sense of how likely they are to commit another offense in case they are released. And the problem is that actually, we don't know if people are going to go and reoffend. The only thing we do know is whether or not once you release somebody, they're going to get rearrested. And so the entire validity of risk assessment instrument is built on how well are arrests a proxy for offense. Okay? Now, while proxies are generally not a problem, they become a really big problem if they're not even proxies, meaning that if two people committed the exact same offense, but their probability of being arrested was not the same because of who they were, then we have a really big problem. Okay, so let's take this as an example. We have two people, they committed the same offense under very similar circumstances, but because of their demographics, because of things they can't change, one of them has a higher risk of arrest than the other person. Now, because risk assessment instruments are actually both trained and validated on these arrest rates, then what you're going to have is that when these people actually end up, in case they end up in court and they are sort of need to in front of the decision of whether or not they're going to be granted bail, the same person that had the original higher probability to end up in court to begin with now also has a higher probability of being denied bail. So basically they're penalized twice, even though they committed the same offense just as the other person. Okay, so this is only a problem if what I'm saying is correct. If the chance of you getting arrested depends on who you are. So let's have a look at whether or not that's true. So the answer is that it really actually depends on the offense. So what you can see here is sort of the risk of arrest, if you like, given that somebody committed simple assault. This is in the US. And actually for simple assault, you can see that the difference, so this is just for men, but the difference based on race and age is pretty much within the error bars. So the arrest rate is pretty consistent. But what happens when we look at offenses like drug use? So here we see a completely different picture where actually, given that two people has committed the exact same offense, the chance of being arrested for it really depends on their age and their race and also their sex, but let's leave that for now. Okay. So what did we do? Basically, the fact that these differential arrest rates really impact risk assessment scores is not something new. We're not the first people to say that. It's been written upon before, but predominantly it's been hypothesized, and to the best of our knowledge, this is the first effort to actually quantify and estimate the extent of this. And so we use several different data sets, so surveys and actual arrest records to sort of compare individuals and do a counterfactual analysis of a matching analysis when you compare people that have the same risk of reoffense rather than the same of risk of rearrest, how different is the risk scores? Okay, and we evaluated this on several different open source risk assessment instrument. And when I say open source, I mean the fact that we knew exactly what their algorithm was, so we can reproduce, given we knew someone's demographic and their arrest records, we can exactly reproduce their risk scores. Now, it's worth highlighting that many risk assessment instruments that are in use are proprietary, they're not open source, and so we don't know what's the situation there. It could be much worse than what we found. Okay. So what data did we use? So we used real but anonymized arrest records from Harris County, Texas, from the NULO dataset. And as a baseline, we did this matching analysis where we took two individuals that had very similar arrest records and the same demographics, and then averaged to see their difference in risk scores. And as you can kind of imagine, actually as a baseline, we didn't see a big difference because those are predominantly the input into the algorithm. So if you're sort of assuming that arrest is a good proxy for offense, everything except for maybe the VPRI is pretty balanced. Everything's fine. Okay? But what was our actual measurement? So we wanted to match individuals not based on the risk of rearrest, but based on their actual risk of committing another offense. And so we needed to estimate their unobserved offenses. So what did we do? So first, we took and overall estimated the unobserved offenses for a demographic group. So we took the number of arrests and we divided it by the arrest rate for that demographic group, and we got a bunch of offenses. Then we needed to assign a portion of those offenses to our cohort. And so we assigned them randomly, but we did use weights based on arrest records. So what do I mean? It means that if I'm assigning an unobserved burglary, non-observed meaning that it was not reported, then I'm more likely to assign it to somebody who was arrested for burglary than somebody that was not. But by how much is a parameter that we varied. Okay, so this gives us, for each person, basically a semi-synthetic offense record rather than arrest record, which is a combination of their actual arrests and then the unobserved offenses that we gave them. So on an individual level, this doesn't mean very much. So of course, we can't tell what are people's unobserved offended, but the assumption is that on a population level, this does represent sort of the offenses in the population. Okay. And so this is the main result. So here we can see the same sort of comparison as the baseline. So we match two people based on their offense record and the demographic, and then we see what is the average difference in the risk scores. And so this is basically, if, for example, for the NCA, if the range of risk is 1 to 5, then the 7% difference, that means on average, Black individuals got 7% of that range higher than white individuals, given they had the same offending profile. And you can see that all risk scores had pretty significant effect that accounts for those differential arrest rates, even though, as I've seen before, this is not true for all offenses. And actually, we have very improportional impact of things like drug offenses. Okay, so when we did these calculations, we did have to make pretty significant modeling assumptions. So first, of course, we have to sort of make some assumption about how much somebody is likely to commit an offense based on their arrest records. We also have to sort of estimate the arrest rate from national estimates. And then we also need to think about the temporal importance of arrest. So like if somebody was arrested for burglary, but it was 10 years ago, does that tell us the same thing about what they're offending now compared to like a year ago? So to take into account all these assumptions, we ran a pretty extensive sensitivity analysis, which is in the paper, and we varied 5 different factors, sort of reran the same analysis. And what we got is that although the numbers change a little bit, actually our result was qualitatively robust, which means all risk assessment scores were sensitive to this effect of differential arrest rates. Thank you for co-authors, thank you for funders, and definitely thank you for you guys for listening.
The first author had to go to another session, couldn't stay, but we have the authors from the other 4 papers. We heard about a matching algorithm and risk assessment instruments in affecting very vulnerable populations, so I think it was a very interesting topic, and I would like to take your questions. Okay. Julia, then.
Question for the LinkedIn doc, which he had to leave. Okay, sorry.
So he had to leave to present a paper in another session. I'm sorry.
Hey, this is a question for the Allegheny Family Screening Tool. So my understanding is that they did quite a bit of what they considered very transparent work and did a lot of independent auditing. And so could you talk a little bit about what you'd rather have seen?
Yeah, that's a great question. I think a huge part of this is, first of all, the reason why we were able to look into this and examine these choices is because of the transparency of the agency here. I think as some of the statistics highlighted earlier in the presentation showed, Allegheny County is not the only county that's using this type of tool, but it's one of the most transparent about this type of process. I think one thing that we think is definitely an output of this work that we think is really important is for the design of these tools to be interrogated in the same way that we interrogate policies, and for the decisions about whether we build the tools, and if so, how we build the tools, to include impacted communities. Yeah.
All right, my question is about the most recent talk with the modeling and the parameter, the sensitivity analysis in particular. So, yeah, you showed that the kind of results were qualitatively robust at different values of the parameters, but I imagine they're quantitatively quite different. And I would suspect that, like, depending on the values of the kind of bias that you see from the model, like that might kind of instigate more or less kind of support for kind of reform in some capacity. So I'm just struggling to think about how you know, you're building a model which has these this nice structure and these assumptions, but given that we kind of can't measure the parameters directly, it's sort of not clear what sort of quantitative conclusions you can draw from that approach. Can you help me think through that?
Yeah, so I think quantitatively it is very hard because it would really depend. So how differential risk rate varies very much locally, but that's very hard to measure well. We just don't have enough data. So we can sort of give an estimate of how bad it is on average, and then some idea of how much worse it can be in some areas. But some of the actionable things is that we do know that for certain offenses, this is particularly bad, is for like drug offenses. So you can make like the policy recommendation that you should exclude certain data points from this analysis that we know are particularly susceptible for those kind of problems. Yeah.
Thank you so much for these presentations. This was a great session. I had a question about the paper around New York City schools, and largely thinking about, thank you. As I understand it, the lottery number was sort of intended to maybe correct for, I think you really beautifully described, I think, many of the inequalities that sort of exist in the New York City housing system. Education system. There's a whole range of screen schools and gifted and talented programs. And as you rightfully noted, you know, it's very resource intensive for so many families to navigate that system. And so I'm just sort of curious if you found in your work, sort of working with parents, whether folks were using the additional information they got about their lottery numbers to sort of reinforce these power dynamics that we know are present in the school search just natively in New York.
So that's a very good question, and it's true. The parents that filled the survey, they were skewed towards higher income and living in richer districts, parents. So the feedback I got was it was helpful for them to avoid being unmatched, but the information didn't give them a better lottery number to get a better match. Now, having that information can actually, if it were used correctly, and if guidance counselor knew about the information, and many guidance counselors don't even know there's a lottery number, it could be used to help improve diversity or help students that are not typically in the popular schools access these schools just by knowing that they have a shot. And that's what has been shown in other work in a different setting, where knowing your test score for some testing schools in various countries can actually help you see the realm of possibilities, because, oh, you did well, and so suddenly you can see yourself in a school that wasn't a possibility before. So right now, the information has mostly, I believe, I don't have that much help people not like readjust their expectations, but it could also help undeserved students access schools that they typically are not applying to just for various reasons.
Hi, my name is Abhishek. My question is particular to the AFST tool, but I think it can be interpreted more generally about how do policymakers or people, decision makers interpret like critique of the New York school lottery system. So two parts. One is that AFST tool still getting used? And if yes, then how has it evolved in the light of all these studies and shortcomings? What has been the learning and sort of actual impact of those changes? Do you know? Thank you.
Yeah, so the model is still being used. There have been different changes to the features in the model, the weights over time, and there are a number of public reports about those changes that sort of explain the logic there. I think there's actually a lot of folks in this room who have also done some of the research evaluating the tool's deployment, who I think can probably also speak to this issue. But in terms of how it's changed over time, I think some of the issues that we highlight here are obviously still relevant and have not necessarily been addressed by the changes.
Question for Gabriel. As a follow-up to that question for Gabriel, so I have heard about the Austrian unemployment algorithm that you described, but I heard conflicting things like, okay, it has been deemed illegal, but it's still in use. That part I don't understand. So the practicality, it is being used, it is illegal, it is what?
So there's a court case that's still going on, and it's being challenged. We had described in the papers in more detail. The argumentation goes that it has no legal basis, and another important point is that the Data Protection Agency are the ones who are challenging it. They're saying that it's because it's like designed as a system to provide recommendations. This sort of allows it to evade certain kinds of regulation. And part of the case is also like arguing that actually it should not be counted as like a purely recommendation-based system, and then like stronger regulations would also apply to it. And the Public Employment Agency is actually lost in the first round. But they challenged that, and it's still an ongoing court case, so we don't know if it will be used. And yeah, from what I know, the idea is not gone, so they're still thinking how to, come up maybe with a different one, but I think now they're waiting for how the courts will settle.
Thank you, very interesting. Let's thank all the speakers again, and with that we can close the session. Thank you very much. Thanks.